Well, thank you very much, Marco. It's really nice to be here. I'm not using my own setup. It's not my laptop and not my remote, so bear with me there, please. I practiced the talk earlier, and I'm running a bit short, but if you have questions, just interrupt me. Just put up your hand. Try to get to you right away, because we might not have time in the end. Also, just meet up with me after the talk or tomorrow. I will be around, so if you have any questions, just ask them whenever. So raise your hand or talk to me after the talk. It's your choice, but I really like some interaction if you can. So let's start with the first slide. All the code I wrote is on GitHub. You can see the link here. It's a bit small maybe, but I'll give you a link if you ask for it. I wrote a small demo implementation of the things I'm talking about. You will see some code in the slides. The code is also with documentation in the demo application. So if you can't really read it that well right now, just go to GitHub and you'll find it. Anyway, let's start with the search topic. Why should you bother doing search? Well, obviously there's Google and those people got a lot of money out of it. But yeah, if you're just a small-time freelancer or whatever, why is it interesting to bother with this? Well, everyone is working with data, and data is only as useful as you can find it, because if you can't find data, it's nothing really. And there's a lot of fragmentation as well. If you're working with some government data from some feed somewhere and you want to combine that with another data source, you need to find out how to crawl that and just combine those data sources into something you can use. Well, also, you guys all write applications, and most of the applications get to a point where they benefit from having some kind of search capability. I guess most of the people here will have used Lucene, or at least considered it. It's a very popular choice for search. And the other point that is something I'm working on with my startup is generic search engines like Google aren't really that great at finding niche data, like product search, for example. So you have of course, Google has a product search feature as well. So you have these niche search engines that do a better job at some specific kind of search. And it's really easy to build those for your specific interest with Clojure. I'll show you in my talk. And then there's also data mining and analytics. There's all sorts of cool stuff you can do with data. Anyway, why Clojure? Because, yeah, why is Clojure the language I picked for doing this? Well, the first most obvious reason is the ability to work with Java libraries like Lucene. It's actually the reason I started using Clojure in the first place. I needed a good excuse to learn a Lisp. This is my first Lisp. I've been doing it for about 1.5 years now. And Clojure was just the obvious choice for me because I didn't want to write Java code. I wanted something more beautiful, more concise. So Clojure is a really good match for that. Now, functional program is also a really good match with the search domain. And of course, Clojure has concurrency. As you all know, it's a typical example of why to use Clojure. And of course, there's the program point where in his essay, Beating the Averages, he says, okay, if you use a language that allows really fast prototyping, you can implement features faster than other people can. So Clojure is very, very nice for that kind of thing. Okay, so what do you need to do with a search engine? It's pretty obvious. You need to get some content. Data retrieval, you need to do a crawl. I guess everyone knows Googlebot. It's the most well-known crawler out there. And then you optionally need to store it. If you want, you can just crawl a new set of data every time you run analytics on your data. But if you are doing something with more than like a few hundred pages, it's really inefficient. So then you do some data storage. You need to do some extraction because you don't want to present plain HTML to people. You need to get some data out of that. Obviously, you need to do indexing, where you feed the data you extracted into Lucene, for example, like we will be doing this talk. And then you perform a search on that index. Lucene, again, provides a very simple way to get a query, run a query against your index. And you need to do some kind of presentation where you write a web app front end, for example, to your search function. So I won't be discussing the presentation in this talk because I just won't have the time. But if you're interested, I wrote a very simple demo in a couple of hours, indexing some blogs, including the blogs of some people here that I found on Planet Clojure. You can test it. It is online. You can find it through the GitHub repository. So check it out. But please don't run the crawl against those blocks like 250 times, which is the amount of people that's in this room. I guess those small blocks won't really handle that traffic well. So be careful with the crawling. Anyway, about crawling, you have lots of very well-known open source crawlers. Apache Nudge is a good example. Same people behind it as Lucene. It's a very obvious choice. You want something scalable over multiple crawling nodes. So if you want to crawl with multiple servers. There's Heritrix, which is written by the people behind the Internet Archive. There's also very scalable, used for very big data. And you have also some really cool Python stuff. I actually started out in search with Scrapy. It's not the most well-known alternative for Python, but it's a really nice way to write your own search crawling framework. And you also have Mechanize, is also a Python option that I personally didn't use, but seems to be very popular. And of course, wget is something most of you will have used. You can use that to crawl as well. And there is an application called httrack, which is also has a GUI. It's nice if you want to do a small scrape. It gets a few pages as a test, if you don't want to bother with a big crawler. Anyway, how do you crawl a page? You have a few steps. You go download a page, a seed page. Obviously, you start somewhere. You need to get an entry point into your data tree. You optionally store that page, like I mentioned before. If you want to do a big crawl, you really need to store stuff. Then you extract links. You can use a selector for that, or you just can get everything. Really depends on your mechanism. You filter those. Optionally, of course, you can do a regular expression or anything really to determine which links to follow and which ones to drop. You download that page, and then you look at the page, run a function over it, and look at the relevance. Is it something that my search engine benefits from having in its index? And if that's true, you start over the same steps, but with the new page that you just found relevant as a seed page for your search. Okay, so there's several ways you can do it already. Discuss some of it. You can do a brute force crawl. Lots of people think that is what Google does, but actually even Google doesn't really brute force everything. They don't index the whole web. They do some sort of filtering. They don't just store everything you throw at them. The direct crawling option, that's really nice for scraping if you have maybe a web shop with some products, you want to get the prices to compare or something. Direct crawling is really nice because if you know the structure of the HTML of a page, you can just tell them, okay, tell your crawler you need to go these steps to find the product pages, and with these selectors you can get the data out of them. That's the easiest and most efficient way to crawl. Well, and there's also what I call weighted crawling, and that's a sort of mix between the brute force and the directed crawling. That's what I use when I don't know as much as I do with directed crawling. But I use a scoring function to determine the relevance of the page. And I give every page I find a score. If it's negative, I stop crawling from that point on. I just ignore that page. If it's 0, I still follow links from that page, but I don't bother storing it for further scraping. And if it gets a good score, I will give it a nice result in my Lucene index. Anyway, lots of good libraries you can use if you want to roll your own. I mentioned some pre-existing crawlers, and obviously you don't need to reinvent the wheel. So if you're smart, you can just look at Apache Nudge, for example. But if you're stubborn like me, you want to try stuff out for yourself before you do that. So there are lots of nice libraries that you can try, and that you can just write some wrapper code, and you pretty much get something in a few hundred lines that works. Clojure, HTTP for getting pages, Enlive and JSON for extracting data, Lucene. I store the data I crawl in CouchDB at the moment. It's not really efficient if you get big data sets, but yeah, we had the Cascalog talks, really interesting stuff. If you want to do something with a lot of pages, use something like Hadoop to distribute the crawling, and HBase or HDFS to store the results. So, of course, there are some considerations when you crawl. You need to be polite. Don't just hammer a page with loads of requests, and don't do stuff that they specifically don't want you to do according to robots.txt. There's also some stuff you need to be aware of. If you start a big process, for example, you don't want to get caught in an endless loop where people generate new links and get your crawler to request them endlessly. You just want to set some sort of max depth crawling level so that doesn't happen. You have people using lots of XML HTTP requests, AJAX stuff. My implementation right now doesn't handle it, but you can use stuff like Selenium to crawl dynamic content as well. Also, user agents, if you use a typical framework, it sets the default user agents. Other people have abused that same software to do nasty stuff to pages. So some webmasters block those user agents. So if you're smart, you don't use the same user agents like Scrapey sets by default, for example. And you can use cloud services to recycle through IP addresses if you get blocked for some weird reason. Anyway, the directed crawl function. This is on the sheet. I hope you can read it. Can you read it in the back? Is it readable? Okay. Well, you have a few arguments. I give a few tags to every crawl I run, so I can use those tags to extract the data later. The external links, the timestamp, the 1000 number is a delay time because you don't want to hammer your target. And then you get some Enlive selectors. The first selector and path filter are a filter you run on the first page. The selector determines which links to get, and the path filter uses a regular expression to filter those links. And then the next key contains a map, or actually a sequence of maps to selectors to run on the next page. And you can chain that and go deeper and deeper into your crawl. So this is something you would use if you would know which data to get, what kind of pages to look for, and store them. It doesn't scrape anything, it's just data retrieval. This is the implementation of the function. I won't go into too much detail because I simply don't have the time. So look up the code on GitHub. It also has documentation. So very short summary is it basically does a recursive loop through the pages, and it runs those filters I mentioned earlier. Okay, then you have another approach, the weighted crawling, where you run a scoring function. And I added an example of a scoring function of this on this slide. You can see it does a count of a search for the word website management in the request key of the body key of the request. So if it doesn't find anything, it will return 0, and otherwise it will get some score, and it will never be negative, so it will never stop crawling. And that's why the second function, it's a link checker. It just returns a Boolean value, true or false. So I limit the search to one domain. It's a plug for my own startup. But yeah, don't run a scoring function that never stops unless you do a link checker on some kind of domain limits or whatever. Anyway, the crawling function, the same thing as with the other crawling function I just showed, where you have directed crawl against page, you know how to deal with. But this function has a few extra values, 3 actually. The 100 number is the max depth. I mentioned it earlier, you don't want to get caught in a loop, so you need to be careful there. I said 100 here, but typically you would use a very small number, maybe 2 or 3. There's the page scoring function, the link checker function that you saw on the previous slide. This is an implementation of the weighted crawl function. Sadly, it doesn't really show on the screen, so just look it up on GitHub. It's pretty straightforward. It doesn't do any really interesting stuff, but it just goes through the pages, runs the scoring function. The only thing to be aware of with this implementation, it's not really smart, because it's multi-threaded. As you can see, there's a future call there. And if it's in, let me check, it's easier to see. Anyway, if it's on a different domain, it runs, it calls the function again in a new thread. So it's not really efficient, especially when you want to detect duplicates. Here I just go to the database and I check if the page is already there. You can see only a few words of that function call, but get page checks if the page is already there in the database. So yeah, it's not very efficient, but you need to get stuff from HTTP anyway, so yeah, speed is not really the most important factor. Well, that's it about crawling. Let's talk about extracting data, because that's arguably a much harder problem. The first note I made is to avoid regular expressions. It's very tempting if you're new at this to just run a regular expression, but the thing is, the structure of code usually doesn't really change that much on an HTML page. But if someone just read a new tutorial and thinks it's cooler to double quote attributes, for example, you need to change your regular expression. And if you're really smart, you will have thought of that in advance, but then your regular expression gets really complicated. So just don't bother. There are very good alternatives, and Enlive is an example, but JSOP soup, I mean, is really good as well. I also already mentioned Selenium for dynamic pages. So yeah, the thing with data extraction, it's really easy, just like with the crawling, if you know what to get and where to get. But if you don't, you need to start doing some cool stuff to figure out what you really need to get, and that's something I won't get into in this talk, but we already had the talk about Keskelok, about core logic. I guess that is a really good starting point, and so is machine learning. There's really cool things you can do to determine which data is relevant. Okay, some examples of Enlive. It's not an Enlive tutorial, but you already saw some Enlive selectors. These are two examples. The last thing, actually, yeah, there you see the A in the vector that just gets all links from that page. The second call is an actual working thing that I tried with my example project. It has a much more complicated selector because I only want to get the links in an element with a sidebar class. That's why the dot is in front of it. In the first UL element, because Enlive enter type sets the number of the element, and then an LI, and then an A tag, and also the first A tag in that. You also can do really interesting selection options with Enlive. Here is the extract and store data function. I use those same tags you saw earlier in the crawling functions with the tags for the crawl, also the database. As you can see, it's called alida here, but you can use whatever database name you want, obviously. The tags are not really interesting, but the function you can see there is, because this function that runs the extraction, you can supply that. It just picks a URI from the JSON map you get back from CouchDB. Then it runs a little helper function which trims the content of the title tag. You can see the helper function in the GitHub repository. And then it runs JSoup to extract the full text, the plain text version of the HTML page. And that is stored in a full text field. It's not really interesting for a production search engine because there's lots of useless stuff in the full text, like the menu and stuff. It isn't filtered out. But for lots of simple stuff, it's enough if you just want to do full text search against, for example, pages. Here's an implementation of the data extraction function. It's also run in a loop, but it processes everything in batches. The default value is 1000. You can set it as well. It's an optional argument, the batch size. It just gets the limit number of pages from the database, and then it does it runs this function over it, the anonymous function, which basically runs the function you provided earlier, but adds some extra keys like the type and URI, which are like internal stuff for CouchDB to run view queries against the search results. Anyway. So if it finds another set, a next page in the map you get back from the CouchDB, it just recurs with the same function over again. It's very simple, till recurs batch processing function. Okay, so the Lucene part. This is something most of you will be familiar with, but some of you will not know that Lucene 4.0 is about to be released. It's a really interesting update. They have been working on a lot of the stuff in this version for a couple of years, but there's a lot of backwards compatibility breakage. So they didn't really want to do those in like 3-point-something releases, and they saved all those interesting big changes for a new release. It is ready for production, in my personal opinion, and it's being used by pretty big users in production already. But the Lucene people are pretty conservative, so it's about to be released, but there's no real date for it yet. But maybe in a couple of months it will be released, but for now, just use it. There might be bugs, but there might be bugs in production versions as well. There's a lot of cool, interesting stuff. I won't go through all of it right now, but they changed a lot about the indexing. It's stored in bytes now, and they improved near real-time search, so you can, if you have a lot of changes in your data, you can do cool stuff with that. All sorts of interesting changes in this new version, so I use that for my demo. A few concepts in Lucene. An analyzer, that's something that tokenizes a string. If you have a text, then you have lots of different word endings and stuff, and tokenization just extracts the stems, the basis of the words from the big text, so you can run a more efficient search. Of course, there are different analyzers for different languages and different types of data, so you can't really use the standard analyzer for Chinese, for example, but for me, for this simple demo, it works fine, but feel free to go through the Lucene repository and find some really interesting stuff there. So directories that are sort of maps to either RAM directories, which are nice for small indexes or file system-based stuff, and the mmap directory is a sort of hybrid between that, where you get the best of both worlds, with memory being used to make things faster, but things being stored on disk as well. I'm using the neo-fs directory because I want this to run on like my MacBook Air with a low amount of memory. And it's a fast way to use a file system-based solution, but it doesn't really work well on Windows, so be aware of that. Yeah, this is a very basic function that creates a directory with only support for these two, but you can obviously change it to get more options. Anyway, index readers. These are ways to interact with the index. Old Lucene had index readers that were read and write, which is a bit weird because it says index reader. But 4.0 changes that, and you use the index reader to read stuff. Yeah, it's very simple as well. You can see the Clojure code there. I don't think I need to explain much about that to this audience. This is the implementation of index writer. Like the name says, it writes to an index. It's also very straightforward, but there are a few things to be aware of. For example, this implementation, just a simple one, because you can do interesting stuff with readers and writers where you wrap those in a manager. So if you have changes in your index, that's detected from your writer. A new reader gets created, but people that are running an existing search still get their old reader. So if you're paging through different result pages of a search query, you don't get the new reader when you go to another page if the data has been changed in the meantime. So you still get the old reader back, which is really useful because otherwise the results aren't consistent. I guess most of this is quite straightforward. One thing here is that you can see I'm running create document from the add documents function in the dosec because it's doing some mutation. I'll get to that later. And the writer needs to be closed, so you run it with open. This is default Clojure way of doing it. Here you see something interesting. Sadly, it doesn't really display well on this sheet, but you basically add a map of the fields to your add documents call. Those fields are used for each document. And this is the field name. Internally, this needs to correspond with the values. And then you use a create field to create the field for that field. And then you have a value, it's a sequence, so you can pass as many values as you have documents for. Okay, so documents. You already saw the call for this, create document. As you can see, there's a mutation here, but it can be converted back to Clojure map. I don't really like dealing with those Java objects in my code, so I just convert it back when I retrieve from the index to a Clojure map. Here's the field type class. Lucene used a field which has a type being passed to it directly, but now it has been separated out into a field type class. Different kind of values. You can see some numeric types. And there are some different options, and those are quite interesting. You have indexed, which means that you can search against that field. You have stored, which means you can retrieve the field value from a document. So if you have search results and you want something displayed there, and you don't want to query your database against your search results, you just store it in the document itself, and you can just display it and access it immediately. Tokenize, it is related to the analyzer stuff I explained earlier. It just tokenizes the text, so that's what you use if you have a full text search on that field. And then freeze, just freezes it. Okay, so create field, it's a multi-method. I really like being able to use something from object-oriented programming here, because I really like the functional style, but this is a really efficient way compared to just making a big conditional structure out of it. It just has, Lucene has different sorts of classes for different sorts of values, so each one has its own solution. Interesting part that I added is a date field, which is basically, you can't really see the implementation, but you can see the interesting, or the useful part at least. It converts a string date in the RC339 format to a long value, which can be queried efficiently in Lucene. Okay, so there is some mutation, like I said. It's a lot more efficient to create your fields once, because if you want to generate 1,000 documents or 5 or 10,000, yeah, it takes a lot of overhead on the JVM to create those fields every time. It's more efficient and recommended by Lucene docs to use mutation to just mutate the fields that you created once. You saw the add documents to index function earlier. It provides a single map of fields and a sequence of maps with the values. Then you have querying. This is a very simple example, but there are lots of different ways to query a document in Lucene. You can check it out in the API docs, but the term query is very simple, just some kind of word or some combination of words against some kind of field. It's the most basic kind of query you can make. Numeric range queries is something else I wanted to show you an example of. It's nice when you want to get documents between two dates, for example. You can see a part of a numeric range query implementation for the date range I just showed you earlier in the field definitions. That just makes the fields are created as long values, and this function converts the input here, start date and end date, back to long values to query against that numeric field. And the same thing goes for the long, float, double, and integer implementations. Anyway, a nice way to do more complicated queries is by using simple ones and chaining them together. So you can chain together multiple term queries or add a date range to it, or if you're doing product search, time range, a price range, or whatever. So you can just chain those queries by creating a Boolean query. I guess the implementation is quite straightforward here. You see the API. You just add the arguments with a keyword, which is, you can see it here. If it's must, it has to be there. If it's must not, it shouldn't be there. And should, then one of the values should be okay in the whole chain, chain, yes. So you can, if you do a search, you provide a query, obviously. You can also filter results, so you can add a filter that just removes some of the documents returned by your query that you're not interested in. This is my favorite way of doing that. Just make a regular query and then wrapping it in a filter wrapper. It's pretty straightforward. Anyway, the search function. Yeah, let's go through this. How much time do we have left, by the way, Marco? Okay, that's good. That's good. I practiced it earlier, and I didn't have. I was way slower then. Anyway, you have some basic arguments: a query, a filter, the field that you want to use as the full text field. I only support one in this implementation. So you have, imagine you have a document with some kind of full text field and some extra fields like a URI, maybe a title, maybe a publication date or whatever. You provide the name of the full text field, full text for example, here in this argument. A limit, which means that you don't get more than X documents back. A reader, which is something you saw earlier. An analyzer, which is a thing you use to tokenize stuff, and some optional values that you can't really see. But you can see the calls here. It's you have search and you have search after. Search after is used when you page through a result set. If you want, you get like the 10th page out of a very huge set of results. You use search after to do that efficiently. So those arguments are optional. Anyway, it creates the different stuff you need. It parses the query. This is a simple if structure. If there's a filter, it adds it here, as you can see. Then it returns a result that is mapped back to this Clojure maps. I don't like dealing with those Lucene documents if I can avoid it at all. So if something goes wrong, it's the query parser accepts all kinds of interesting arguments where you do like a star asterisk sign to whatever. Anyway, you can also make syntax errors in that. This catches that, and if there are no results, you just get the empty map back. But if you if the search contains a bad query, you just get nil as a result. So you can differentiate between that. Okay, that's it for my talk. I do have something else which I can show you quickly. That is the demo implementation I made. Do I have time for that? Okay. Well, it's not my laptop, so let me be really fast. In the meantime, does anyone have questions while I do this? Because I don't think it really, the screen size is pretty bad. You can just, if you go to the GitHub repository, there's a link as well. So I can't really get this on the screen right now. Any questions? Sorry, I can't really hear you. In this implementation, there's not much internationalization going on, but internationalization is mostly done with the analyzers. So, of course, the two things you can do with, you can tokenize differently using different analyzer. What Google does is they, for example, if you're searching from a certain location, it adds a bonus to local pages. So you can also with Lucene do custom scoring, and you can just add, for example, an extra few credits to a page that's local to the searcher. Okay. Any more questions? Or?
No. Okay.
Okay. Thanks.
So, thanks.